Hey, this is from the worksheet on fluid mechanics. So a solid ball weighs 5 Newton in air, 3 Newtons when submerged in water. That means that the up thrust, okay, is equals to 2 Newton. So when in this unknown liquid, the up thrust is now 3 Newton. Okay, so up thrust formula is equals to V rho G. Okay, V, remember, is the weight of the fluid displaced, but when it is fully submerged, the volume is equals to the volume of the ball. So we have this thing called V, the density of water G equals to 2.0. You also have V, density of liquid G equals to 3.0. Now, then comes this term called specific gravity. What is specific gravity? Okay, basically, it is the ratio. Okay, let me just step it out so that you can see. It is the ratio of the density of the object to the density of water. Okay, that's the meaning of specific gravity. So in other words, we want to find what is density of this divided by this. So you can see that if I take equation 2 divided by equation 1, I get density of the liquid, unknown liquid, over the density of water equals to 3 over 2, which is 1.5. So this is the specific gravity. So answer is D. Okay, next question. Suppose two plates of a balance scale are in equilibrium while the scale is kept under water. Okay, so now at here they are in equilibrium. It's 1 kg of iron, unknown mercury. Okay, density of iron is given. Mercury not given. They're given, but the volume not given. So when you lift it up the water, what will happen? Okay. So now in each of this case, okay, this is balanced. What causes it to be balanced? Okay, it's a downwards force on each one. So the downwards force, okay, if we look at it and you look at the balance in each way, normally we say that the weight causes it to be balanced or unbalanced, right? Because the weight exerts a force on the balance. So let's just draw this instead of a curved shape. Let me draw a flat shape. So when I have the object on top, right, we say it's weight. It's not really because of weight. Now, when there's weight, right, and it's at rest, there's a normal contact force upwards. So on this, there's a normal contact force downwards. Okay, so it is the end that's downwards on each side that is equal in magnitude that causes it to be equilibrium. Okay, when this is equidistance, okay, it is the downwards end. And that is what we are going to tackle here. Now, for each of this case, okay, when it's balanced, we know that the end is going to be the same. So let's look at the free body diagram of the iron and the mercury. So on the iron, there is upwards end, there is up thrust for iron F, and then there's weight of the iron. Whereas for the mercury, the end is the same when it's in water. Okay, plus the up thrust due to mercury equals to the weight of the mercury. Okay, so you can see that the end is the same, okay, which means that when it act on the balance downwards, it will be balanced. So now what happened is that N plus the up thrust equals to the weight. Okay, and N plus the up thrust equals to the weight. Then they are still in equilibrium individually. Now, when it's taken up in the air, this one and this one disappears. Okay, the upthrust is due to the water, so it disappears. Okay. So how do we then balance it again? Now, what will be lacking is we don't have the actual weight because we have the density. But to get the weight, which means we need to get the mass, we need to get the volume. And to get the volume, okay, for the iron, it's straightforward. It's going to be 1 kg. Okay, we don't know the mass of the mercury, and that's what we need to find. And that comes from finding the volume. So that comes from here. Okay, so we can see that because the N is the same, the weight of the iron minus this is equals to the weight of mercury minus the upthrust on mercury. Okay, because N is the same. Weight of iron, 1 times 9.81 minus V, density of iron, G, equals to weight of mercury. Let's put as weight of mercury will be volume times density of mercury times G. Okay, this is actually mass. Volume times density is mass. Okay, put this as V2. Okay, this one put it as V1. Minus V2, density of water, G. This upthrust on the mercury. Now, first thing, why I want to put like in this way, because I can cancel the G out. So I don't deal with so many decimals. So 1 minus the volume is actually density over, you can take volume as density over mass over density. Okay, 1 over 7870. Density of water. Okay, it's not, if I'm not wrong, this should be given in the list of constants. Okay, so it will be actually 1000 equals V2, density of mercury, which is 13550, minus 1000. Okay. Okay, so if you press on your calculator, you'll get your V2 as 6.9556. No, 6.955, no, 6.956 times 10 to the power of minus 5 meters cubed. So that's the volume of the mercury, which means that the mass of the mercury is density times volume. You'll get 0.942 kg. Okay, so one side now you want to balance in air. One side 1 kg, one side 0.942 kg. So to balance the the balance, you need to add 1 minus 0.942 kg to the mercury side, which is 0.058 kg or 58 grams. So we need to add 58 grams to the mercury side, which is the right side. So answer is D. Okay, so that is the working here. Okay, we'll go on to the next one. Now, a beaker, base 40 cm square, contains water to a depth, certain depth. Okay, a small block of dimensions 4 by 4 by 4 is placed in the beaker, and the rise in the water is 1.2 cm. Now, the thing is that we don't know if this is floating inside. Okay, or sinking. Most likely it's going to be floating. If not, they will ask you the question. So the rise in water is 1.2 cm, which means that the volume displaced is 1.2 times 40. Okay, so 1.2 times 40 gives you 48 cm cube. So you can see it's floating because this is actually 64 cm cube. So because it's floating, up thrust equals weight. Now the water, again, the water, we need to take it from a list of constants. Okay, it'll be given to you 1000 kg per meters cube. So up thrust, 0g, 48 over 10 power 6. This is converting to meters cube. 1000 g is equals to 64 density of the block times g. So cancel, 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 cancel. We want to find the density of the block with that of water. Okay, let's because it's asking us for that of water, I can just use the density of water. Okay, so we don't really need the density of water, we just need in terms of it. Okay, so the density of the block is equals to 48 over 64, the density of water. 48 divided by 64 gives you 0.75. So answer is D. Okay, so this is pretty straightforward. Okay, next question. Question 11. Okay, 2012, question 45. So the water level in a reservoir is maintained at a constant level. What is the exit velocity in an outlet 3 meters below the water surface? Okay. So this question, right, although I put it under fluid mechanics, it is actually a question on work energy power. Okay, you can see that it's at a constant level, 3 meters height, exit velocity. So there is a loss in GPE, which is equal to the gain in KE. That's all. MGH equals to half MV squared, or V equals to square root of 2GH. So you take a square root of 2 times 9.81 times H, and then you get 7.67. Okay, meters per second. So answer is D. Question 12. This is a more interesting question. A U-shaped glass tube consists of 2 open-ended vertical glass tubes. Okay, so a length of 2h is joined by 2h, and diameter is much smaller than h. So the volume is not going to change much, I think. Okay, so we can ignore the diameter. So the horizontal tube is initially filled with mercury of density rho, and the atmospheric pressure is rho naught. Subsequently, the 2 ends are sealed. Okay, so here are sealed, but the air inside is still the same. The tube is accelerated towards the right, and the mercury then occupies a length of 5/3 h inside the horizontal tube. So now it is turned to 5/3 h, which means that here it must be 1/3 h. Okay, because the tube, okay, it moves all the way, the 1/3 h move out. Okay, so what is the acceleration now? So what happens is that we are probably going to be more interested in this segment of tube here, easy to see. Okay, why? Because there's a force by this top part here. It exerts a pressure, it exerts a force that will cause it to accelerate. Now, this top part here we can ignore because the sides of the tube, which is this side, will be able to accelerate it. So we can ignore that. Okay, so we just look at this H over 3 part. Now, so the concepts that we need for this question, right? Okay, is actually basically just P1 V1 equals to P2 V2. Okay, so this comes from Boyle's law. For O levels, what happened is that you all only learn the qualitative aspect, which means you just need to say that when temperature is constant, the pressure is inversely proportional to the volume. But what does it mean by inverse proportion? It means this. P1 V1 equals to P2 V2. Okay. The other one that we need is H rho G, and we also need F equals to MA. So now, when we look at this segment here, okay, this is just 5/3 H. We want to look at the forces on the left side or on the right side. Now, what happens is that we have this part of the air that is compressed, and this part of the air now becomes longer. Okay, it extends to here. So we let the new pressure here, we let the new pressure be P1 and we let the new pressure be P2. Okay, so we have our P1, P0, the original pressure. Okay, original pressure is P0. P0 V, original volume, let it be V, equals to P1 2/3 V. Okay, that's for the left side. So we get our P1 as 3 over 2 P0. Similarly, P0 V is equals to P2 now is going to be 4 over 3 V because it increases by 1/3 V. Okay, 1/3 H is same as 1/3 V here because common the same cross-sectional area throughout. So this is going to be 3/4 P0. And due to this, the pressure, due to this extra mercury here, okay, maybe due to mercury, is going to be H rho G. Okay, so now you have all the pressures ready. You can look at this segment of the mercury, okay, the 5/3 H part. So our forces here and the forces here, the two forces here is due to the pressure of P1 and the pressure of the mercury. Okay, and the other side is due to P2. So P2 times A, cross-sectional area, let it be A. This is going to be P1 plus PHG times A. So the resultant force, P1 plus PHG minus P2 times A is the resultant force, is equal to the mass times acceleration. What's the mass? 5 over 3H times A, that is the volume of that mercury, times density. Okay, so this is the mass, A. So this is F equals MA. Now we sub in everything slowly. So 3 over 2 P0 plus H over 3 rho G minus 3/4 P0 is equals to 5HA rho over 3 times A. Okay, so now just I forgot to multiply by the A here. I combine already, okay, and then we need to multiply by A. So now what happens is that we are going to cancel off the A. Okay, it was the common cross-sectional area. Now rearrange. Okay, you'll get that. You'll get 3 over 2 minus 3/4. You get 3/4 P0 plus H rho G over 3 divide by 5 rho H over 3. That's our acceleration. Now you multiply by the common denominator. Okay, 4 times 3, multiply by 12 over 12. So when you do that, this one you get 9 P0. This one you get 4 H rho G over 20 rho H. That is your acceleration. So you go back and check. Okay, so only answer E fits the answer that we have here. Okay, now we zoom out a little bit. Okay, let's go to the next question. 2013 question 42. If you ever had to wade across a rocky creek while hiking in the mountains, you will have probably noticed that by the time you get to deep water in the center of the creek, the rocks do not seem to hurt your bare feet as much. So what's the reason? Now, the reason it will hurt is because you exert force on the rig and the rocks, and the rocks exert a force on you. Okay, so when the force the rocks exert on you is large enough, it will definitely hurt more. Okay, that's common sense. So why deep water comes in is because when you go to deep water, there will be upthrust. The upthrust is going to be larger because more of you is going to be within the water. More of you will displace the water. The upthrust on you is larger. So the force that the rocks exert on you upwards down will be smaller. Okay, so now we go through each of the choices. The greater pressure on one's feet in deep water means the rocks cannot dig in so much. I think the greater pressure they mean is that the HOG is larger, but that's not really true. Okay, just that so it's like water pressure, right? Is that the pressure at the bottom is larger, but the pressure at the top is lower. See, so that is why there's upthrust on you. So A is wrong. Right? I don't know what they really mean, but yeah, it's wrong. The velocity of water in deep region is less. It's less in deep region as not going to affect much. Okay. One tends to stand in deep water. If you reduce the area, the pressure is going to be larger. Okay, so cannot be. Deeper water is colder and hence more dense. Now, the density of water doesn't change much, regardless of the temperature. It does change, definitely does change, because that's why you get convection current. Okay, but the change is not so significant that it's going to affect much here. So unlikely to be D. So one experiences a greater buoyant force in deeper water, which is the reason why there'll be less normal force. So let's say this is your leg, the weight of the leg, the end, and the upthrust. So it is the upthrust that is larger that causes the end to be smaller because your W stays the same. Okay, so answer is E. Okay, then next one, question 18. Question 2015, question 3. Okay, so for this question, two bulbs X and Y connected by a tube P as shown. Both bulbs have different air pressure. Which of the following are possible? So there's non-zero pressure. Let's call this P naught. Okay, we don't know the pressure. But what happens is that at this point and at this point, they have the same pressure. I mean, here and here is 16,000. Here and here is going to be 8,000. Okay, we don't know H1 and H2. So this is air. This is, they did not give this. Oh yeah, they gave mercury. Okay, the density of mercury, 13550 kg per meters cube. Okay, by right, it should be given in the least circumstance at the front. So what happens at here, at this point, is that P naught plus H1 rho G is equal to 16,000. And at this point, P naught plus H2 rho G equals to 8,000. So we can see that if we take equation 1 minus equation 2, H1 minus H2 rho G is equals to 8,000. Okay, the P naught cancels out. So your H1 must be larger than H2. Okay, so that already tells you E is wrong, C is wrong, A is wrong. You're left with B and D. Okay, so if we use this, okay, you'll get H1 minus H2 equals to 0.06, which is around 6 cm. But you'll realize that none of the answers here have 6 cm difference, okay? And I just checked on the 2015 paper, this wasn't even given. So you're supposed to do this question without knowing this. Okay, so if we don't know this, we will not be able to get this. Okay, which means we need a second method. So hey, this elimination is still needed. Then comes the second part. You'll realize that if I take this number 1, okay, this 1 minus 2, 1 minus 2 times 2, 2 times equation 2. I will get negative P naught plus H1 minus 2H2 rho G equals to 0, or H1 minus 2H2 rho G equals to P naught, which is non-zero. Now, if P naught is 0, H1 equals to 2H2. That's actually answer B. But P naught, not 0. Therefore, H1 must be greater than 2H2. So actually, you will see that none of the answers fit. So this question, right, actually not possible to be done. Okay, although the answer is D, this is the official answer given, but this question is not doable in this case. Okay. So that is for this question. Okay, next. Okay, the question is not doable. I just put it here. Not doable. Okay, just here for you to see how not doable is, so you can actually see, to think through a little bit. Okay, so next one. Okay, so now we are here for circuits. Question 1. This is very O levels. So I hope you all can see that this, if I zoom in a little bit, this circuit, the 6 ohms here, is in series with the whole set of parallel. Okay, these 3 highlighted ones are all in parallel. They tell you that going through here is 3 amperes, which means that this must be 6 volts. So this one must be 2 amperes, so that is still 6 volts. And this one must be 1 ampere, so that is 6 volts. So add up, it must be 6 amperes, which means that at here, it must be 36 volts. So here, 6 volts, here 36 volts, add up, 42 volts. Answer B. Okay, this is pretty O level. Okay, next one. A resistor has a resistance R and a battery has an internal resistance. Now, internal resistance first, let me just explain this one first. A battery itself, right? Okay, normally an ideal battery, you all draw at O level, it's just a battery itself. But a non-ideal battery is that it has a mini resistor inside because of its inefficiencies. So when you draw a battery, right, it's actually like dotted like that. Then after that, there is an internal resistance that can never be taken out. So what you can do when you see internal resistance is just to treat it like as a resistor in series with the battery that you can never remove. Okay, so and you put any voltmeter, you always be outside. You can never go parallel to this battery. That's all. Okay, it's like a casing. The resistors inside the EMF battery casing. Okay, so when the resistor is connected, this big R is connected across the battery, 10% less power is dissipated across R. That will be dissipated. It has no internal resistance. What is the ratio? So they are trying to say that, okay, now we have two circuits. R, let this be EMF, versus we have internal resistance small r, and then here. The power here is, you can just take as V square over R, EMF square over R. Now, in this case, we need to consider by potential divider rule. What's the potential difference? Or we can just P equals IV, also can. So if it's I, it's going to be this. And the power dissipated is equals to I square R. Not IV, I square R. So I square R will just be square over R plus R squared. And now they say that 10% less power is dissipated in this. Okay, so 10% less. That means that this power is 0.9 times of this because 10% less. Cancel this. R squared equals 0.9 R plus R squared. Okay, technically you can expand it, but what I will like is to like make it simple. R equals to just square root both sides. Okay, square root 0.9, 0.94868 R plus 0.94868 a small r. Okay. Okay, to be more proper, it's actually going to be this or the negative version. Of course, the resistor is not negative, so this one you reject. Okay, so that's why you can just do this. Now, if you bring over 0.051317 big R equals to 0.94868 small r. So small r over big R, bring over. Okay, divide by 0.9486. You get 0.054. So answer is going to be E. Okay, so 0.054. Answer E. Okay, hope it helps you.